We will continue with the lecture on inverse response systems and controlling inverse response systems. In the last class, I explained what inverse response means and how you identify inverse response systems by looking at the transfer function model. Just as a quick recap, inverse response systems are systems where the initial direction of change is different from the final change. So, assuming that we start deviation variable at a value 0, if the final value that the variable takes, for example, in response to a step in the input, if it is positive. However, if the initial slope is negative, that means it is going to be taking certain negative values for at least the initial part before it is going to turn back and then go and take a positive value. So, this is what we call as inverse response systems, and I described in an example, an engineering example of an inverse response system, which is a boiler, and I also mentioned there are several other systems which show this inverse response. And we also saw that you can quite easily identify if there is inverse response by looking at the transfer function. So, for the first time we start focusing more carefully on the numerator transfer function, and if the numerator has what we call as a right of plane 0, then we can say that the system will have inverse response. And a generalization of this is where I said if there are odd number of right of plane zeros in the numerator of the transfer function, then we will have inverse response. And then I also try to explain to you why inverse response systems are difficult to control. I talked about a bike where you want to turn right, but it initially turns left, which will make you get really confused, and then the control becomes hard because you do not know after it turns left when is it going to come back to right and so on. So, that is the physical reason why control of inverse response systems become complicated. And that is also very nicely seen in a direct synthesis approach, and there I said, if you remember, the controller formula in direct synthesis approach is 1 over transfer function of the model GM times G desired divided by 1 minus G desired, and because we are inverting the process model, any right of plane 0 in the process will become a right of plane pole in the controller. So, if you want to get an ideal response, whatever that you desire, then that would mean that you will have to have a controller which has to act without stability, and that is never a good. Basically what this essentially means is then that somehow you have to take care of this, and that somehow is in actually modifying our expectation for what G desired can be. So, till now we have never put any constraints on G desired. We said you choose any G desired you want, but now we will have to start enforcing constraints on G desired, and we will have to see how we enforce a constraint on G desired, so that we do not design a controller that becomes unstable. So, that is a key idea. Now, let us understand how this is done mathematically, but before we do that, let us think about the example that I talked about in the last lecture, the bike example, and then say, look, if you already knew that if you turn the steering right, the bike is going to turn left for a short bit of time, and this is a problem that you have to somehow handle. You still have to turn right. You also know, though it turns left for a short bit of time, it will ultimately turn right. And if this is the case, then what is the best solution that you can think of in terms of the control problem? The best solution would be in modifying what our notion of the desired response of the system is. So, if I know that the bike is going to turn left for a short bit, and I still have a G desired where I say, okay, whenever I want to turn right, I should immediately turn right. So, that is a G desired which is unconstrained. I can ask for anything, and I am going to ask for the fact that whenever I turn right, I should turn right, though the system itself is prone to go left for a little bit before coming right. I say I do not want it, right. Now, that is not possible, both mathematically and physically you can see this. So, another approach might be understanding that the system does have inverse response. What you could simply say is, okay, I know that when I turn right, I have to be completely turning right at all time as a G desired transfer function is not possible. So, maybe what I should do is I should say, okay, let me make a compromise. I definitely do know that once I turn right, after a while the bike is going to turn right. So, maybe what I am going to do is I am going to live with the inconvenience of turning left for a short bit before the bike does exactly what I want it to do. So, that is the basic idea of modifying the G desired, so that we still have a stable controller. Okay. So, what we are going to do is we are going to tolerate this inverse response a little bit in our G desired that we ask the closed loop system to follow. So, that is a basic fundamental idea in solving this problem. So, this basically says, okay, if I have a performance limitation in terms of RHP 0, then the ultimate closed loop performance will suffer a little, but I know that I am going to tolerate this, and I really do not worry about getting the best performance that I specify in an unconstrained fashion. Okay. So, let us see how all of this works out in terms of the math that underlies these ideas. So, I already talked about the controller form, which is G desired divided by G model times 1 minus G desired. So, the numerator of this G model is basically the one that constrains the performance. Okay. So, let us take an example and see if what happens here. If you have the G model like this, and looking at this, you can say that there is going to be inverse response behavior, and you are going to say that there is an inverse response behavior because the 0 of this transfer function is s equal to 1 over 1.5, which is in the RHP. You also notice that all the poles are in the left half plane, s is minus half, s is minus 1 over 3 and s is minus 1 over 5. This is the reason why I am going to get an inverse response. Okay. Now, if I use this G desired, which I have chosen here for example, and then say let me go ahead and compute this C, you will see that this C will become unstable because this will go into the denominator here. So, I have in the denominator polynomial a right half plane pole which will make the controller unstable. So, this is something that we need to avoid. So, this is what we talked about till now. So, how do I avoid this? So, I avoid this by saying that I will have to give up something in terms of my G desired. My ideal G desired was this, but I am going to give up something by actually including a right half plane 0 in the G desired. Basically what I am saying is I am going to modify my expectation, and I am going to assume that I will have inverse response in the G desired also. Why would I have inverse response here? Because just like how we analyzed here, if we analyze this transfer function here, this G desired transfer function has a right half plane 0. That means the G desired itself will show you inverse response. So, basically what we are saying is we are completely translating whatever I told you physically into mathematics. I said if I want to turn right, if I had just only this, then I say I want to always turn right. I do not ever want to turn left, right, if my final intention is turning right. However, we knew that it was not possible. So, the sensible thing to do is to turn your steering right and wait and do nothing. The system will turn left for a bit and then start turning right, right. So, that means in the performance you couldn't stop the bike from turning left a little bit, and that we actually deliberately introduce ourselves in this G desired and then say okay, this is fine, okay, because this is something that I am going to give up. And I am going to show you what happens when I give this up in terms of performance drop. I will now get a controller which is stable. So, now with this G desired I go back to this same equation here and then put this here. So, this is my G desired, this is my GM, and this is my 1 minus G desired. Now, if I do the algebra, the key thing that you want to notice here is that because this 1 over GM gets me this right half plane 0 in the transfer function to become a pole, that pole is going to be cancelled by the 0 that I have introduced in the G desired, because G desired is in the numerator. So, this and this will get cancelled, and that is how we get rid of this problem of instability of the controller when we introduce this inverse response behavior in G desired. Now, once you do this, and there is a reason why I have chosen this 9s square plus 3s plus 1, because by choosing that I can get a control form which is of the PID controller form. Okay. So, this is again just to remind you again, this is Kc divided by 1 by 1 plus 1 by tau is plus tau ds, right. Now, Kc is 8 by 13.5, tau I is 8, and tau d is 15/8. So, basically what this allows us to do is it allows us to design a PID controller for inverse response system. So, it is still in the form that we are comfortable with. However, there is an understanding that we are losing certain performance, and that performance loss is actually deliberately introduced by us in this G desired transfer function, so as to keep this controller stable. Notice in doing this, we have a stable controller, get reasonable performance, and we get a PID controller. So, traditionally, people have been using PID controller for inverse response systems, and you kind of ask, why does it work reasonably well? And here is the math that shows why it works reasonably well, if you are able to, or if you are ready to give up a little bit on the performance that you require out of these systems. Now, mathematically, another interesting thing that you should notice here is that I am cancelling, if you look at the controller transfer function, I am cancelling 0 of the controller transfer function, because this is in the numerator of the transfer function with a pole of the same transfer function. So, if I look at the controller transfer function, I am doing what is called a pole 0 cancellation. Now, whenever people do this pole 0 cancellation, they always worry about this, because like I said before, if you get some stability using a pole 0 cancellation, and if the model is not good representation of the process, and actually the 0 of the actual process is not the same as the model, then would this still work in real life, is always a worry that people have. So, in this case, you got to remember something, and when we moved away from the traditional undergrad control topics to more advanced topics, such as the one that I am teaching here, I said for the first time we are going to think about a model and the process as distinct transfer functions. We want the G model to be actually equal to GP, in which case there is no process model mismatch. However, in reality, GP will be slightly different from G model. So, we have to be very careful when we think about these calculations to understand where we are using G model and where we are using GP, because traditionally, till we came to this direct synthesis, and then I started talking about model and inverting a model and so on, we typically say, okay, here is a G process, design a controller based on the G process, and then put the same G process transfer function in your closed loop block diagram, and then see how well it does. Okay. So, in that case, we are intuitively or implicitly assuming that the process and the model transfer functions are the same. However, I started making this distinction about model here when we started doing the direct synthesis approach, because irrespective of what G process is, what we are saying is I have an idea of a model for the process, and I am going to make all my judgments based on the model itself. So, here I am saying, okay, this is the transfer function model for the process, and I am going to make all my controller decisions based on this model. So, this model is actually a conceptualization. The true process could actually be something, okay, just to make a point, okay. So, I could have something like this, 2s plus 1, 3s plus 1, 5s plus 1. So, the true process could be very same structure, the denominator being the same, but the numerator is slightly different from this 1 minus 1.5s, this is 1 minus alpha s, maybe alpha is 1.6 and so on, right. So, there could be a mismatch between G process and G model, but this does not come into this computation, because the controller computation is always done using the model, right. So, whatever this alpha is, I have already conceptualized the model as being this, and I have already conceptualized that the RHP 0 is at s equal to 1 over 1.5. Okay, so that is already decided. So, even if the true process is not exactly the same as the model, the controller does not change, because the controller works only with the model. While it looks like a simple concept here, many times you can miss this, because if I simply asked you this question, oh, you did all this controller and did this pole 0 cancellation, but what if the process is slightly different from this? Will the controller become stable, and will this pole 0 cancellation not work? So, the answer is the pole 0 cancellation will always work in this case, because I am anyway going to work with a model, and irrespective of what value alpha takes, I am going to use this model transfer function. So, as long as I use this model transfer function, I use this G desired, this and this will get cancelled, and I will get this PID control. Now, then, so you might ask, okay, if that is the case, then what is the impact of process model mismatch? So, the impact of process model mismatch you study now. When you put this controller in your closed loop block diagram, you use this G process, right. So, the controller has been designed assuming the model is this, but actually you check the effect or the performance of this controller on the process, which could be different from the model you used here in designing the controller. So, that will be realistic, where okay, you go to a plant, you have a concept of a model and then use that model to design a controller, but when you finally test the controller is being tested in a real plant where the process could be different from the model. In fact, the process could be grossly different from the model, then you will have more difficulties, but if it maintains the same structure, but let us say if this is the only thing that changes, then we could ask what happens to the performance. Now, what will happen to the performance is interesting. So, for example, if I have let us say a closed loop, now let us say I have this controller that I have designed, okay. I have let us say this G process. So, the standard control loop diagram we will do, I have this set point, I have this negative, I have this coming here, going here, and I have a Y here. Now, it will turn out that you design this controller based on whatever model you have assumed, okay. And basically what you are saying is, I am going to really look at the closed loop transfer function, which is GPC by 1 plus GPC, which is G desired, right. Now, when I am actually designing the controller, I am replacing this GP by GM, because I have to do it only with the model, I cannot do it with the true process, right. So, I do GMC by 1 plus GMC equal to G desired, okay. So, basically this G desired will give you some Y desired. Now, if this process and model are the same, the Y you get here will be exactly the Y desired, or this G desired and this will be the same, okay. However, you design a controller based on some model and then you actually put it into a process, and the process is slightly different from your model, then this controller was designed using this equation, but the true closed loop behavior is basically GPC by 1 plus GPC. Now, G desired GMC by 1 plus GMC, so that need not be the same as GPC by 1 plus GPC. So, the true performance that you get while you implement this controller in a process is going to be given by this. This is the closed loop transfer function, and this need not be exactly equal to G desired, and it will in fact be equal to G desired only if GP is exactly GM. So, that way this framework brings in the idea of a model, a controller based on a model, and then the specification or the performance of the controller when it is actually implemented on a true process. Now, the true process is also represented by a transfer function form. So, the way in theory you will use this is, you could say okay, this is the model, but let us say the transfer function form for the process is drastically different, what will happen. So, those kinds of studies you can do using simulations, and ultimately the proof of all of this is when you take this controller and implement it in a true process and how well it does. And if the variety of G process models that you have tested to check the robustness of the controller spans the whole gamut of the process operations, then you would have a priori a very good idea of how your controller will work when you actually put it into real process, okay. So, this is a very important idea that you should understand well, okay. So, the controller is always based on a model, and the closed loop performance is based on the true process, and when we want to do all of this studies theoretically, the process model we keep it as something which can be different from the model that we use to design the controller, and the G process, by varying several parameters in the G process which is different from the G model, you can see the robustness of the controller. So, in the next slide I will show you an example where assume that you have, this is the model and then you designed your controller, but let us assume the process itself is slightly different, its RHP 0 is at some other location. Now, we might ask the question what will happen, right, how will the performance change, I am doing a pole 0 cancellation, will I still have a stable closed loop and so on, how much uncertainty can I have in this value while I still maintain my closed loop to be stable. So, these are things that we can see. I am going to show this to you, but it is important to kind of take a step back and then think about this and understand this well. So, that we think about these pole 0 cancellations and we think about when they will have an effect, when they will not have an effect. So, here clearly I will show you it is not a big problem here, but there is a case where you will see that these pole 0 cancellations could have big effect on the stability and the robustness of the closed loop. Okay. So, we will get to that later, but let us look at this and then look at this right here and then process, which is this, but let us assume we had used a model to design the controller, which is 1 minus 1.5s divided by 2s plus 1, 3s plus 1 and 5s plus 1. Let us say this is a model that is used to design the controller. So, if I use this model to design the controller, I already know the controller form, which is basically this 8 by 13.5 times 1 plus 1 over 8s plus 15 by 5 or 15 by 8 times s. Okay. So, now when you look at the closed loop system, what you will do is the G closed loop, okay, is going to be equal to GPC. Okay. So, GP has to be now 3 times 1 minus alpha s divided by 2s plus 1, 3s plus 1, 5s plus 1 GP times the same controller that we derived from the last time. Now, notice that this controller does not change because this is based on this model. Okay. So, I use the same controller here and then I do this 1 plus GPC. Now, and this GP is again this thing right here. Now, if this GP is GM, that is alpha is 1.5 in this, then you will get this to be the G desired that we had designed the controller for. But if the alpha is different from 1.5, then you will get a slightly different closed loop which will not be exactly G desired. So, that is where I first made an accommodation in the G desired for the inverse response. Okay. So, that is already incorporated, and even after this accommodation I will not exactly get what I desire because of the plant model uncertainty. So, the first is actually making allowance for the difficult to control components in the model, and the second thing is when the actual process is slightly different from the model, then you lose little more performance. So, that GCL will be different from the G desired that we specified, right, because that difference comes because we calculate the controller using G model here, but the true closed loop is G process times C divided by 1 plus GPC. Now, if you do all of this algebra and then come up with the closed loop transfer function, and now you ask this question. So, I did a pole 0 cancellation, I assume that the zeros location is 1.5, but the true 0 location has changed to alpha, which is as yet unspecified here. So, I might want to ask the question, if this alpha is slightly different from 1.5, let us say it is 1.6, would my system become unstable because I have done a pole 0 cancellation, is a worry that you might have, and we will see what happens here. Okay. So, basically what we are seeing here is what is the amount of uncertainty that I can tolerate in this alpha, how different can it be from this 1.5 while I still maintain stability is the question that I am going to ask. Of course, we have already said that because this G closed loop uses this GP, it is not going to be equal to G desired. Okay. So, the loss in performance is already there, which is the difference between G closed loop and G desired in some sense. So, performance loss because of model plant mismatch is okay, but I do not want the system to become unstable because of this plant model mismatch. So, I should also judge whether that there is a possibility of that happening. So, to check that, what we should do is this GPC divided by 1 plus GPC, same thing, you do all this algebra and then you will get the denominator polynomial, and the denominator polynomial will turn out to be this. Now, this is a quadratic, and you know the quadratic root you will have minus b plus or minus root of b squared minus 4ac by 2a, and if a is positive, this b term is the only thing that decides the location in terms of right half plane or left half plane, and in this case in fact if this 13.5 minus 3 alpha greater than 0, then we can guarantee that all the roots of this quadratic are in the left half plane, because this will be positive, 27 is positive. So, b by 2a is positive. So, the roots will be minus b by 2a. So, that will be in the left half plane. Okay. So, for this to be positive, I should have 13.5 minus 3 alpha greater than 0. So, I could take 13.5 is greater than 3 alpha, that makes alpha less than 4.5. So, as long as alpha is less than 4.5, the roots of the denominator polynomial of this closed loop transfer function will all be in the left half plane and the system will be stable. So, what this basically says is if this were 4.5 and I still guess this to be 1.5, I will still be stable. So, there is a tremendous amount of error that I can actually accommodate in the identification of the location of RHP 0. So, what this basically says is you do not have to really worry about pole 0 cancellations in this case, unless of course you have grossly underestimated or overestimated the RHP location. So, in other words, it has to be very different from whatever value you have taken in the model. Okay. So, this is how we look at how to tune and derive controllers for inverse response systems. The key ideas are to enable us to design a controller. We introduce some performance laws in our desired transfer function, and then we were able to design a controller which turned out to be in this case a PID form. And then we also discussed whether the pole 0 cancellation will have any effect, and I showed here that you could grossly misestimate the RHP 0 and still stability problems will not be there. Clearly performance comes down to two factors. The first factor is actually the difficult to control dynamics, which is the inverse response, because of which we made some allowances in our G decide itself, that is number 1. And number 2, if the G process is different from G model, the closed loop transfer function is going to be different from G decide, that is other loss of performance, which is notionally the difference between G CL and G decide. So, you can see how this idea of direct synthesis allows us to so clearly understand where performance limiting factors come in and how you avoid those performance limiting factors and still design a controller. The only thing is the trade off is you are going to get a constrained G decide. You cannot choose any G decide you want, you still have to obey certain rules, and your constraint or some other components are necessarily added to a G decide, which is something you would not have added by yourself. So, that is something that is important to understand. Another important thing as we go forward, because you can see the slight shift in the way I start talking about controllers and control design. In the first part we did not make such a big deal about the difference between a process and model, but as soon as we came into this direct synthesis and started moving on to more advanced topics, we talk more about a model and then we kind of differentiate between the model and the process, and then we made the point the controller design is all based on notion of a model, but the true effect of the controller, if you want to study, then in the closed loop you have to use the process transfer function to study the effect. So, this notion of model and predicting something with the model or designing a controller based on a model is going to be a key idea that takes you from your standard undergrad controller to more sophisticated controller. So, one last thing that I would like to address here is I do not want you to get the feeling that we are not using a model at all in your undergrad control. We do use a model. Where we use the model is in designing the controller. For example, if you take Ziegler-Nichols tuning, you use a model to figure out what is the limit of stability, and then all your controller tuning parameters become a function of the model parameters in some sense. Whereas, slightly conceptually different is this controller itself having the direct model equations into its design, like C is 1 over G M D G decide by 1 minus G decide is slightly different. Okay. So, in the other case also model parameters are very much there, but they get buried into your PID controller. Here it is more explicit, and as you go, you will see as you go more and more advanced in control topics, it will become more and more explicit in the controller calculations themselves. So, even here for example, though I say the controller is 1 over GM and that is where the model explicitly comes, ultimately we got a PID controller. So, all the parameters were used and implementation is PID. So, this is, while it is little more explicit than your Ziegler-Nichols tuning, it is not used in online controller computations. I mean, when I say it, I am talking about the model is not being used, but in the next thing which we are going to talk about, which is how do you control time delay systems, you will see that the use of the model will be more explicit even in the controller calculation. So, you cannot simply live with the PID, but on top of a PID you will see that there is some model related terms that come in the controller computations online. So, without the model you cannot implement the controller. In the other case, once the controller is designed, you can directly implement it. Okay. So, you are going to see that this explicit use of the model keeps increasing more and more when you go into the more advanced control topics, and ultimately the kind of pinnacle of this is actually using the model in an online optimization framework to do computations, which is what model predictive controller is, which we are going to talk about. So, that is also a nice progression in terms of ideas that I would like you guys to think about. So, I will get back in the next lecture to talk about time delay systems and what are the difficulties that time delay systems introduce and how do we control time delay systems. Thank you.